Hey there, Adrian Rosebrock here from PyImageSearch.com, and today we're going to be talking about regression with neural networks. So far in our study of deep learning, we've predominantly focused on the concept of classification. So that's when you have a set of labels and you train a model to predict one or more of those labels. But the problem with a label is that it's not a continuous value, it's just a single label. What if you wanted to predict the actual continuous variable like the price of a home, the age of a person, what you think the stock market is going to do? That's an example of regression because you're not just limited to a set of variables. You're actually interested in predicting a singular value, but that value could span over a wide range of possible values. So again, we've focused predominantly on classification. We're now going to start talking a little bit about regression and how regression works in terms of neural networks. And furthermore, this will help set the stage when we start looking at more advanced deep learning techniques such as object detection. Because state-of-the-art object detection algorithms actually have two heads to the neural networks. One head is classification. It's responsible for predicting the class label of the object that it's detecting. And the other head is actually a regression head. It's responsible for it saying, hey, these are the bounding box coordinates of where the object is. Now, you don't frame object detection in the form of classification. Otherwise, you would have one possible value for every single combination of XY coordinates. That's not reasonable. Instead, what you use is regression to predict those XY coordinates. But before we get there, let's study the basics of regression first. Specifically, we'll be looking at regression through the concept of predicting the price of a home. So inside this tutorial, we have this example image here of what of classification versus regression looks like. So if we were to use classification to predict the price of a home, we would have these input attributes. This would be, the square footage of the bedroom, the square footage of the kitchen, the number of bedrooms, the number of bathrooms, the zip code, things like that. So you would have these categorical attributes, some of them real valued, some of them categorical. They go through this classification network, and then you predict a set of class labels. And the labels could be very cheap, affordable, expensive, or very expensive. Well, that's fine for simple categorization, but what if you wanted to predict the actual price? For example, $407,000. Well, you would start with those same attributes, and your network would look pretty similar, except there'd be a slight change at the head of the network. And then from there, you'd be able to predict the actual price of the home. So that's what we're going to be doing here today. We have this example house prices data set that includes 4 numerical and categorical attributes: number of bedrooms, number of bathrooms, the area and square footage, and your zip code. And this is from a 2016 paper by Ahmed and Mustafa. So there are 535 data points in this data set. And what's cool is it's going to allow us to study regression in terms of basic neural networks, in terms of convolutional neural networks, and then combining both image data with this numerical and categorical data. Because when you dig into this data set, what you're going to find is it's more than just a CSV file of this data. It also includes images of the bedrooms, the bathrooms, the kitchen, and the exterior of the home. So it's a really, really cool data set to study for you to learn about regression in both neural networks and convolutional neural networks. So I have a project directory structure pulled up over here, and you'll see we have a single Python script today, mlp regression.py. It's going to load our houses data set, and it's going to construct a multi-layer perceptron and perform regression on it in order to predict the price of the home. Now inside the PyImageSearch module, we got 2 files to review today. Datasets.py is just a little helper utility that parses the house dataset file. And then models.py contains our MLP model definition file. The houses dataset here is stored in our project directory structure. And as I say in the tutorial, you can clone it down from GitHub and then just move the dataset into our Keras regression project directory. But inside of it, you'll see we have a whole bunch of images. And look at the naming convention of these images: 1_bathroom, 1_bedroom, 1_frontal, and 1_kitchen. That implies that these 4 images pertain to the same house. So here is the bathroom of one of the houses, here's the bedroom, the exterior, and the kitchen. Now this house here starts with 2. It has a unique identifier 2. So these 4 images belong to the second house, and so on and so forth for all 535 houses in the data set. But we're not going to work with image data just yet. We're going to start working with that in the next tutorial in the series. What I want to draw your attention to is this house info.txt file. This contains all of the attributes that I was telling you about right up here. So inside this text file, for each house you have the number of bedrooms, the number of bathrooms, the area and square footage, the zip code of the home, and then the listed price of the home. So our goal is to take these 4 attributes and construct a neural network that's capable of predicting the list price of the home. So that's pretty much it from a project directory structure. Let's learn how we can actually implement this using neural networks. I got my project directory structure pulled up here. And let's take a look at the datasets.py file, because this is arguably the most important one for loading the data, pre-processing it, and then once the data is loaded, it's actually a pretty simple training procedure. So we start off with our imports. We have our label encoder here. We use that on the zip codes. We have min-max scaling, and that's going to take, I'm going to show you this. It's going to take each column here, so number of bedrooms, number of bathrooms, and it's going to scale it. It's going to find the max value and the min value in each of these individual columns here, and then scale them to the range 0 to 1. We do that 0 to 1 scaling. It's a pretty standard pre-processing procedure for working with neural networks. We have pandas, so we can easily load the CSV file and parse it. And then we have numpy for numerical array pre-processing. I also have some unused imports here. And that's because in the next tutorial in the series, we're going to build on these functions and create some functions for loading those images in the houses data set that I was telling you about. So these imports will go unused for now, but we'll use them in the next tutorial. From there, we have this load house attributes function, and this is going to load this .txt file from disk. So what we do is we accept the input path to that text file, and we define the columns for the text file. So the columns here are bedroom, bathrooms, area, zip code, and price, as we previously discussed. We read this CSV file from disk using space as the separator, because that's what the separator is here, and we pass in the name of our columns. Now, there is a bit of class imbalance in this data set, specifically with the zip code. It's in fact extremely imbalanced. There's data samples here that only have 1 or 2 houses per zip code. So in order to make this a bit of an easier problem, we're going to discard some houses if the number of houses in that zip code is below 25 data points. Now, we can talk about how to handle class imbalance, different techniques you can apply, but that is really a separate series or a separate set of classes and courses in PyImageSearch University. This is really focusing on just regression. So let's learn how to apply regression first, and then we can start worrying about class imbalance. So this line of code here grabs all unique zip codes inside of our data frame that we read from disk. And then we want to count the number of unique zip codes. Having this count here will allow us to filter out houses that have a small count associated with them, a small number of houses that belong to a particular zip code. So that's what this code here is doing. We're going to loop over each of the individual zip codes, and inside this count variable contains the total number of houses that belong to that zip code. If there are less than 25 homes that belong to that zip code, then we're just going to delete them and drop them from our data frame. We're not going to worry about the class imbalance there. Let's only work with houses that have a significant or a substantial number of instances that belong to that particular zip code. Otherwise, like I said, it becomes a class imbalance problem, and we're just not ready to study that yet. So at this point, we've loaded the CSV file from disk. It exists as a pandas data frame, and then we've done some basic processing here on the data just by removing homes with low zip code counts. The next step is to actually process these attributes and prepare them such that we can pass them through a neural network. So here we have column names that are continuous data points. So the number of bedrooms, number of bathrooms, and square footage area, that's essentially an integer or a real value data point. You could have anywhere from 0 to infinity technically for each of these. I don't think you wouldn't really see a home with a thousand bedrooms unless you're living in a hotel or something. But my point is that there are technically infinite number of values for the number of bedrooms, number of bathrooms, and the square footage area. On the other hand, the zip code is not a continuous value. This is a categorical value, so we have to encode them different. So for the continuous values, we're going to use our min-max scaler, and we're going to find the minimum and maximum values inside each of these individual columns, and then scale them to the range 0 to 1. If you've never used min-max scaling before, it's a really, really simple procedure. And really all you're doing is you're going to compute the min of x across your column, and then subtract your original data point value. For example, let's assume we're examining the value 4. Then it's be 4 minus whatever the minimum value in this column is. And then you're going to divide by whatever the maximum value in this column is, subtracted by the minimum value in the column. That's all min-max scaling is doing. It's pretty simple, pretty standard preprocessing procedure. Now we do one hot encoding on our zip codes. And let's take a second now. Our goal is to get all features in that'll be passed through the neural network in the range 0 to 1. Well, by definition, with min-max scaling, we know these continuous values are inside the range 0 to 1. And using a label binarizer here, by definition, that one hot encoding procedure, by definition, ensures that these values also exist in the range 0 to 1. So the next step to do is just to concatenate our encoded categorical values and our continuous values together. That's all you have to do. That forms our feature vector of scaled continuous values and our one hot encoded zip code values. These form our features that'll be passed into our neural network that'll allow us to predict this column here, which is the price value of the home. So these are our helper utilities. They're responsible for loading our house info file from disk. So let's implement the model itself. So I'm going to open up models.py into PyCharm, and we'll start off with our imports. And you'll notice the vast majority of these are not used. We're only using the sequential class and the dense class. So why have I imported batch normalization and convolution and all of these others? Well, as I said, we're going to start working with image data in the next tutorial in the series. So we'll not only be relying on these house attributes, the number of bedrooms, number of bathrooms, but also these example images of the homes as well. So these imports are just placeholders for what's coming in the next series in this tutorial. Let's now create our multi-layer perceptron via the create MLP function. We have the dimensions here. This is the length of the feature vector coming into the neural network that came out of the process attribute function. So it's basically the length of this list here, the concatenation of the categorical values and the continuous values. And then we have this regress Boolean. If we are performing regression, we'll set this value to true. It's set to false by default because, again, next week we're going to do some pretty cool stuff, and the following week as well, where we start combining both categorical and continuous data with image data and train a network on both of those. But for now, you'll see when we instantiate the MLP, the regress value is going to be set to true because, again, by definition, we're performing regression with this multi-layer perceptron. So we initialize the model, and then from there, we have a fully connected layer with 8 nodes, followed by a ReLU activation. Then we have another fully connected layer with 4 nodes, followed by a ReLU activation. And in the event that we're performing regression, we're going to add a single fully connected layer with 1 node and a linear activation function. This 1 node here corresponds to the target value that we want to predict, which again is the price of the home. So that's why we have this singular node here. Now, why linear activation? Why wouldn't you pass in a ReLU? Well, that's whenever you apply a regression, that linear activation is going to be pretty standard and pretty important, especially in the context of what we're doing here. So the goal is, keep in mind that we're going to have all of these house prices scaled to the range 0 to 1. So that means our linear activation value is going to be between 0 to 1. And that is a good purpose for the linear activation function, because we're not trying to follow a sigmoid activation. We don't want to use the ReLU either because of the potential of negative values. So whenever you perform regression, especially for this kind of house price prediction, you're going to use a linear activation function. Let's put all these pieces together now and open up MLP regression.py. We start off with our imports. We'll use the Atom optimizer for training the model. We have the train test split function for creating our training and testing sets. We have the datasets utility that we just implemented that'll load and pre-process our categorical and continuous data from the house prices. We have the models module, which contains our implementation of the MLP. And here's NumPy for numerical array preprocessing, argument parsing. We'll use locale for displaying a nicely formatted price to our screen. Just makes it a little easier to parse through the results in the terminal. And then we have OS here as well for operating system specific functions. The only argument we need here is dataset, which is the path to our houses dataset residing on disk, which will be this directory right here. And then from here, we construct the path to our housesinfo.txt file. This is the text file we want to parse and extract all of the categorical data, the continuous values, and the target prediction price of the house. We then load the house attributes from disk, and as we'll see, we'll also pre-process them. But before we get to that, let's perform our training and testing split. So we'll use 25% of our data for testing and 75% for training. Now, the next step is to scale the price value to the range 0 to 1. So we find the maximum price value in our train set, and then we'll divide the price column by this max value, therefore ensuring all prices lie in the range 0 to 1. So that's what these two lines of code are doing. Just like we pre-process these columns here, the number of bedrooms, number of bathrooms, square footage, and zip code, such that those values lie in the range 0 to 1, we do the same thing here. And we do that to reduce the number of degrees of freedom inside the network when we go to train it. Once we have our training and testing splits and we've performed our price scaling, we're now going to pre-process our house attributes via our process house attributes function here. So that's again, we're doing min-max scaling to our bedrooms, bathrooms, and area columns, and then we're going to do one-hot encoding on our zip codes. All of that gets concatenated together and then returned to the calling function right here. So at this point, our data set is ready to go. So we create an instance of our multi-layer perceptron, and notice that regress is set to true. That's because we're going to be performing regression. We then use Atom as our optimizer and then compile the model. For loss, you have a number of different loss methods here. You could use mean squared error, mean absolute error, and both of those would be perfectly fine choices. But for this particular problem, I actually like mean absolute percentage error because it's going to make it easier for us to interpret the results of our output. And I'll explain that in just a second. So once our model has been compiled, we then train it for 200 epochs with a batch size of 8. These hyperparameters were just tested empirically by us in order to find the best values that give us reasonable results. And once the model is trained, we make predictions on our testing set. So these predictions will contain the prices of the homes based off of the number of bedrooms, bathrooms, square footage, and zip code. So now we start to get into our metrics here. So what we want to do is compute the difference between the predicted house prices and the actual house prices. So the predictions here is a list, and we want to subtract the true ground truth regression value, the actual price of the home, from the predicted price of the home. And by doing that, we can compute the percentage difference between the two. And if you take the absolute value, that gives us the absolute percentage value. So we're doing our own evaluation here, just like we monitored and optimized the loss for mean absolute percentage error. This is what we're doing now. We're evaluating the predictions of the model based off of mean absolute percentage error. Then we compute the mean and the standard deviation of the absolute percentage difference, and then display the average house price, and the standard deviation of the house price. So when we go to run this script, all you got to do is copy and paste the usage, paste it into your terminal, and then run the script. You'll see our data set is loaded from disk, and then we train our model for 200 epochs. And given how simple this model is, it can train really, really quickly, even on your CPU. So I want to scroll down to the results section of this guide so we can kind of review this together. Looking at our output here, you can see at the bottom that we're getting about a mean absolute error difference of about 27% and a standard deviation of 25.43%, which is slightly different than the results here just due to the stochastic nature of neural networks along with differing TensorFlow and Keras versions. So what does this result mean? Well, it implies that on average, our model will be off by about 27.83% in either direction, assuming a bell curve. It'll be off by about 27.83% in terms of house price prediction. And the standard deviation will be about 25.43%. Now, that's okay. That's a good start, but that really wouldn't be used in like your popular applications and websites used for listing homes for sale. That's not anywhere near of enough of a correct prediction. So how can we improve upon that? Well, one of the issues here is it just a limitation of the house price data set itself. We only have 4 attributes: the number of bedrooms, bathrooms, area, and zip code. The Boston house price data set, on the other hand, this has over 14 attributes, and the popular Ames house data set has 79 different attributes. So these data sets are doing a much better job of representing and quantifying not only the home, but the area in which the home resides. Because you could build a beautiful multi-million-dollar mansion, but if you place it in an area that's not very nice and not very that someone who could afford a house like that would want to live in, well, the home really isn't worth what they put into building it. And this data set that we're using here, it doesn't really capture those nuances. But that's fine because our goal here is first and foremost just to understand the fundamentals of regression in neural networks. But after that, the goal is to learn how we can combine regression with convolutional neural networks, which is why we have all these images of the homes. And then finally, what we're going to do at the end of this tutorial, or at the end of this series, is we're going to take our images and our categorical and continuous values, the bedrooms, bathrooms, area, zip code, combine them together and create a convolutional neural network that's capable of accepting 2 different diverse types of data sets, training the model for regression, and as we'll see, we'll be able to improve our prediction accuracy. So this will be a really good series of tutorials for you. You'll not only gain experience with a regression, but you'll get experience with multi-inputs to neural networks as well. So download the code to this post, go through the Jupyter notebook, make sure you understand the fundamentals of regression. At the very least, all you really need to understand is what's contained in this image right here. If you're performing classification, you're predicting a discrete set of possible output class labels. Regression, on the other hand, is producing a continuous value. It's predicting a continuous variable. So while the output of a classification network could be very cheap, affordable, expensive, or very expensive, our regression network gives us the actual price of the home. So we're going to build on this in the next 2 tutorials in this series. So make sure you go through this one carefully. Make sure you understand the basics, and I'll see you next time.